That's the problem. Okay, let's get started today. So today's an important lecture. Limits. So limits are basically the most important thing, most important tool, most important framework for doing calculus. And why is this the case? Well, I'm just going to write a motivating example. We're going to return to it later. Motivating example. Okay, so later on in this course, we're going to be interested in something called the tangent line. I'm sure you've all seen it. So we want to be able to look at this point here and find its tangent. This is the tangent of f. And the tangent has a bunch of nice properties, right? We can read a lot of information off tangents. And slope tells us if we have increasing or decreasing information, but the thing I'm mostly interested in, which we'll flesh out more, is that if you take a curve and you look at it really close, it looks like a line. You should have discovered this when you were working through that sine x worksheet. That sine x near 0 is just the line. So it turns out this is true on every function. And the line that you get by looking very close at the function is the tangent line itself. So suffice it to say, these tangents are going to be something that we need to calculate. Now, does anyone remember how we get a tangent? Well, so a tangent, it turns out, is obtained by taking the limit of secants. So that means we're going to have some type of graph. And we're going to want the tangent point here. And we're going to find the tangent line, rather, by finding the limit of these secants. I'm going to find a point that's a little bit away from here. And I'm going to connect them. Okay? And what I'm going to do, so I have this point P, and I have this point Q. What I'm going to do is I'm going to move these points closer and closer together and calculate this line. And eventually, you're going to have the line of the tangent. Now, so we need some way of saying, so we want to move P close to, but not equal to Q. Okay? So again, I want to be able to, so this is the geometry of it. I want to put a point here, I want to put a point here, I want to run a line through those 2 points, and just keep calculating those lines as I move this Q closer to this P. Why is it important that Q, did I reverse this? Yeah, I think I did. It's just reversed from the picture. Right, so I'm trying to move Q towards P. Why is it important in this example that Q can't be equal to P? So ask yourself, what am I using P and Q to do in this case? Yes, sir? Yeah, I'm using P and Q to form a line. How many points do you need to form a line? 2. Therefore, if I can't put Q on top of P, they can't be the same point. I can't draw a line between one point and the same point. Right? So I need some way of saying, I want some way of saying geometrically that I want to move this point Q on top of P. I want to move there, but assume you never get there. You can't ever actually be equal to P. Right? Otherwise, I can't form the line. So this is an important property about the limit. You're asking, well, we'll flesh this out more, but you're never actually obtaining, you're never actually setting x, let's say, to the point which it's limiting to. It's an important property that we're excluding the limiting point. But we're going to talk about this way more detailed. For now, so this class is going to be broken into 2 pieces, as normal. Okay? We're going to talk about limits geometrically. That is, we're going to talk about limits by looking at the graphs. And we're going to find that that's very easy. Then we're going to have to talk about why that's going to be insufficient. and then develop some algebraic tools for dealing with the limit. So the first half of this lecture is going to be the geometry of limits. So geometry of limits. So I want to look at this problem. Let us investigate this function. Did anyone bring a calculator? Did anyone bring a cell phone? Yeah, now I know you're lying. Did someone just get prepared? Okay, so forget about these tangents. This is now sort of starting afresh. We're just going to look at this function. I don't want to plot it because that's going to give away a lot of the story. So what I want to do is use a calculator and start computing points of this just to experiment with it. Like suppose you wanted to draw this. That would require us to find like maybe 600 points and draw a curve through it. So who would like to be my helper for extra marks on the exam? Do you have a calculator ready to go? Okay. So I just want you to get ready to calculate this. So just prepare yourself for that. I'm going to do the first few. So I'm going to draw a table here. This is going to be the table for x. This is going to be the table for f evaluated at x. And what I want to do, so let us investigate this function near x equals 0, right? So what is the value of this function if I put 0 in? This is important. Maybe I'll ask this question on your midterm.
It's undefined.
Undefined. Why is it undefined?
The denominator will be 0.
Better than that.
Vertical asymptote.
0 is not in the domain of this function. There is no rule taking 0 to anything. That's illegal, right? So this function is just not defined at 0, but that doesn't eliminate it or exclude it from having behavior at 0, which we'll find out. Okay, so I want to investigate this function when x is near 0, but I can't put in 0. The function explodes, right? If you put it into your calculator, I think it would just burst into flames. Okay, so let's do this. So if x is 1, what's f of x? Oh yeah, we can. Can you tell me?
Yeah, I'm doing it.
Okay. Well, you just tell me if you get this. Okay, I'm going to draw a few more. 0.1. This is 0.049999. 0.001. That's going to be 0.050000. And now 0.0001. Can anyone evaluate this guy at this number? 3 zeros, then a 1.
I don't know how to, it's just not giving me a stupid space. Like,
Okay, that's okay, that's okay. I actually have them written here. But I just wanted someone to discover something. Could someone please evaluate this on their calculator at that point while I go enjoy a sip of refreshing coffee? And I'll be embarrassed if it doesn't work. Yes? 0 is what your calculator will give you. But if I gave you a better calculator, it would report this. If you put it into Google, for example, if you use the Google's calculator, you would get this number. Okay. Your calculator only works to like 10 digits. This problem is already outside the numerical realm of your calculator. Right? So this was a lie. If you put in 0.0001 into this, your calculator will report 0, which is wrong. The true value is, well, this is not even necessarily the true value, but if your calculator was capable of working with more digits, you would get this. So I'm going to strike here and just make a warning. Right? Calculator may report 0. But it's a lie. just broken. And so be wary of your calculator. Your tools can report incorrect things. Okay, so we go from 1, I divide by 10, I get 0.1, I divide by 100, I get 0.001, 0.0001. So I'm just, can you see that these numbers are getting closer and closer to 0?
Yes.
So these numbers are getting closer and closer to 0. What's the F value? What's the mapping getting closer to?
0.05.
0.05. So let me write this in the table. I could say maybe we go, if we continue this and we actually get to 0, I'm going to speculate that this goes to 0.05, which is what? 5 over 100? Is that correct? Yes, 5 over 100. Let's look at the other side now. This is f of x. So let's do negative values. So let's see. What do I get for, I'm gonna move up this time, it will make more sense. So if I put in 1, minus 1, what do I get? You have to think smart, not hard.
Minus 0.049876.
It's exactly this, yeah?
Yeah.
How did you know that?
What's the limit? It's approaching from both sides. No.
That's closer. This is an even function, yeah? The values at positive x are the same as the values at negative x. Look, x is squared in both cases. Right, so that means that if I give you negative 1, it becomes 1. If I give you positive 1, it becomes 1. That happens on both sides. So I can look at this graph, see that it's even, and then I don't have to recalculate all of these values, because I know that negative 1 will go here. 0.049876. I'm just going to skip them. So I'm just going to go down to the 0.0001 here, the negative case. And this is going to go to 0.05. And then this is going to limit maybe to 0. And we're going to get 0.05, which is 5 over 100. Okay. So this is how you understand. So you have to understand that this is geometric. Right? When we look at a plot, we're looking at individual points that have been drawn. These are also individual points that have been drawn. You can write these dots on a graph paper, and then you'd have the picture. But this fundamentally is the limit calculation. Right? We want to take x's closer and closer and closer to some limiting point, and we want to investigate the behavior of f. Okay? So you learned a little bit about this in high school. So this is us getting to 0 from the positive end. So this actually here is called, and we'll flesh this out a bit more, the right limit. And this thing here is called the left limit. Oh, I have no fun problems for you to think about. Need to hire one of you just to chase me and wipe down the board. So we should have probably made a concluding statement up there. So I'll do that right now. Okay. So for that example, we say, So for that example, we say here that, okay, because this is a lot of information that's on the board, and we're going to talk about this type of procedure a lot. So I said usually when it's the case that we have to do something a lot, that it gets a special notation so we can more quickly talk about it. So rather than me waving my arms around and saying, well, I want to investigate the behavior as x is doing this and look at what's happening to the mapping, we simply encode all of that into the statement. The limit as x goes to 0 of x squared plus 100 minus 10 over x squared is equal to 5 100ths. Okay? So this expression is sort of codifying everything that I've written on the board on top. This is a statement saying that you can expect some type of limiting behavior like this. Okay, so I'm going to give you the definition for limit, but it's not the real definition. Okay, I'm going to give you a good enough definition that we're going to be able to use, and then I'm going to show you the strict definition, but you're not to panic. It's not something that you're going to need to know, but you should at least see it once, in my opinion. So let's have sort of provisional, operative definition of the limit, so loose. So this is the one that you will be using. We say the limit of x goes to a of f of x is equal to L when, and this is going to be very wordy, when f of x becomes arbitrarily close to L when x is sufficiently close to but not equal to A, or on both sides. Okay, so digest that a bit. But fundamentally this is saying, look, your mapping, your function, is doing something in the range. So suppose you say, I have f, I claim that the limit of f goes to L when x goes to A. That means that, okay, so these are why I underline these two words, arbitrary and sufficient. Arbitrary means for any of them. So an adversary chooses this. They say, look, if this is true, then you should be able to put f arbitrarily close to L. Right, which means that you should find x small enough so that you're not too far away from L. Right? So we found x, so 1 up there is pretty close to the limit. So if I said, show me that the limit is within 0.01 of the value f of 1, it would be true. It's like these limits are sort of hard to describe. I don't like this one. I'm going to draw you the strict one. I think that's easier to understand, but you don't have to understand it or use it. But this is the actual definition of the limit. This is one of the differences between this course and the science course. Okay, so again, not testable. Okay, I'm not testing you on this. Testable. Okay? This is hard to work with. I struggled with this. All of my colleagues struggled with understanding this limit definition. It is tough. But if we think of what we're trying to say, we're saying, look, this function is going to try to get to L. And it should, if you're telling me it's limiting to L, the function should, if I want you to get 1 over 100th close to the limit, you should be able to do that. If I want you to get 1 over 1,000th close to the limit, you should be able to do that. In fact, for any tiny arbitrary small number, you should be able to restrict x to a region where the function is no more than a little bit away from the limit itself. So, here we go, and don't panic. And again, the definitions are hard to understand, but like actually doing questions is sort of easy. So, the limit of x goes to A is equal to L when, okay, and here's where I'm going to convert this English to symbols, which I like better. For any arbitrarily tiny number, this is called epsilon. It's a Greek letter. This other one is called delta. It's another Greek letter. Little delta. You're probably used to big delta. Okay, so the limit, I have to give it a limit of f goes to L. I should be much more explicit than this. Limit x to A of f of x is equal to L when, for any arbitrarily small number epsilon, there is a delta greater than 0. Okay, so this is hard to understand perhaps, but the order of these symbols matter. Okay, this means someone else chooses a tiny number, and then you get to choose a tiny delta based on that tiny number. And it's the fact that these are ordered this way which enables the limit calculation to work. But I'm going to give you this definition. So the limit of f of x, as x goes to a of L, is equal to L when, for any tiny number epsilon, there is another tiny number delta, such that if x is restricted to this domain, a minus delta, a union a plus delta, then f of x is going to be restricted to this domain. L plus epsilon, sorry, L minus epsilon, L plus epsilon. Okay, so I don't think this is beyond our ability to comprehend. So what is this interval I wrote here? I'm going to draw some pictures. So if this is A, and I wrote it like a union, right? So I can explicitly exclude A. X cannot obtain A. I put it on the open boundary on both of these, right? Otherwise, I just would have wrote A minus delta to A plus delta. But this is an interval that excludes A, so I removed it. So if this is the real line, okay, this means that you're going to have an X in here, and this is going to be A plus delta, A minus delta. And as delta gets smaller, this interval becomes smaller as well. And what I'm saying is, I'm going to draw this number line. So this was the x-axis. Now this is the y-axis where the range is. You should see that if x is in, this is the tiniest of all pictures, but just look at my slides. You should see if that x is in here, that the function y is also going to be restricted on this axis to this interval. So if this is L, you're going to have L plus epsilon here, L minus epsilon. So what happens is that someone says, look, if you're claiming that the function's limit at A goes to L, then that means if I give you an arbitrarily tiny interval about the limit on the range, you should tell me what arbitrarily small interval you have on the domain. Okay, so if that all went over your head, who cares? You don't need to know it. I just wanted at least once to open up the trunk of the car. Trunk? What's the front part? Hood. Hood of the car, so you could see the machinery of this, right? Because when we continue, we're going to be reading a bunch of stuff off of graphs, but in mathematics, nothing is simply true because, right? Everything that I'm going to show you today can be deduced absolutely logically from algebra. I can do all of this algebraically. That's called the real analysis. And it's not that useful, because not everyone needs to look under the hood. But this is an English description that should be good enough. This is the strict definition that we're not supposed to show you, but you should see it at least once. Notice that this interval along the x-axis is broken into two pieces. That's why you get a left limit and a right limit. You can read most of it from the strict definition. So again, don't stress too much. You are not supposed to know this. I'm not even supposed to show it to you. But you should know it exists. So just try and digest it a bit. That'll be the hardest part of this half of the lecture, because you don't actually really need to use that definition. Because we'll never actually ask you to prove something's the limit. Okay, limits are usually easy to find when you have a graph. All right, so here's an example. Let's say that this is, what did I say this was? This is x minus 1 cubed plus 1. That means that this point here should be what? This is the inflection point of the cubic. This should be 1, 1. Right, because this is a rightward shift and this is an upward shift. Right, so 1 right, 1 up. Okay, what is, so from graph, what is the limit as x goes to 1, as x minus 1 cubed plus 1? What is it? Okay, so I know you know how to do this. I know most of you have now just taken this one and plopped it into there and calculated it and said it's 0. But just forget everything your high school teachers have taught you, because I'm only going to use the stuff that I've shown you already to demonstrate things I'm writing on the board. So don't do this algebraically, right? Because all I've given you, like I shouldn't have even given you this really. But I have to, then otherwise I would have had to label like a ton of points. But in any case, so we want to ask, as we approach x equals 1 here, what does the function approach? So you can see this limit calculation as sort of just like walking along this curve. Right? And you're like, oh, I seem to be always walking. If I restrict myself to this path, then I'm heading to this point 1, 1, whose ranged component is 1. Right? So I'm walking, I'm walking, I'm walking. I never seem to get there, but I do seem to be heading towards 1, 1. The same is true if I walk around here. You're heading to 1, 1. Right? So just like you take a little walk along the graph, and you're like, I seem to be heading there. But remember, I specified that you never actually get to the point itself, which is an important property that we'll need later. So if you walk towards, if I'm walking this way, which is towards this point, where am I approaching on the line? What is the limit of this function as I approach x?
1.
1. This one, not that one. That should be more careful with these examples. I just want to add a little bit of notation. Okay? When we say x single arrow a, so you may have noticed that my inference symbols use double arrows. It's because we have a different arrow with one arrow that's this. This reads, okay? This reads x gets arbitrarily close to a, but not equal to. Okay, so this really has like a strict meaning. Okay, let's do another example. All right, so that's what this says. It says, as x gets arbitrarily close to but not equal to 1, this value goes to 1. Here's another question. Example. Let's look at this function. F of x is equal to x squared minus 1, x minus 1. And let's find the limit as x goes to 1 of this function. Okay, so first of all, tell me what f of 1 is.
Undefined because it's not included in the
Yeah,
domain.
undefined, right? I'm not asking you trick questions. 1 is like, you have to look at this and immediately say, oh, notice 1 is not in the domain of this function. Right? So we can't evaluate it. But that's okay, because the limit doesn't actually ever set this function to 1. So I'm going to draw you the picture of this. It looks like this. So first of all, I know that there's here at x equals 1, there should be an open circle on that line. Otherwise, this just is a line like this. And this is going to be an open circle, 1, 2. Okay, so what then, so from the graph, what is the limit of x goes to 1 of this function?
2.
Yeah, 2, right? So you're walking along this guy. So as you walk along here, you're getting closer to the x-axis. And as you walk along here, you're getting closer to 2. And the same is true from the other end. So if I gave you an equation or a graph, if I said, find the limit of the following function, and I offered you the equation or the graph of a picture of it, which would you take? Graph. It's always easy to read these things off a graph. If I ever ask you to find the limit of a graph on a midterm, those are free grades. I'm just giving them all out, right? So please earn the freebies that I'm trying to throw at you. Oh boy. Pour coffee. All right, so ponder, construct questions. You guys should be asking tons of questions. Oh, by the way, I have to cancel my office hours tomorrow because I have to teach the night class. So I'm going to need some rest. What if you want to come in on Friday? You're welcome to. Okay, what is next? Okay. Here's an example. It's going to be, what is the limit of x goes to 0 of sine x over x? So, how would you do this algebraically? If I asked you this, right? So I'm going to give you a picture. Can you do this yet? What happens if you try to put x equals 0 into here?
Undefined.
Undefined, right? 0 is not in the domain of this function, so you can't even ask for it. Okay, so now we're basically restricted to experimental guesses, right? That's essentially what looking at the graph means. So provided I tell you that this is the case, so I'm just going to look at this function very close. So this is going to be -1 to 1, so I'm not even writing a whole period of this function. It kind of looks like this. It has an open circle here, right? Because you're not supposed to have definition. And I'm going to tell you that point here is 0, 1. So class, read for me from the graph this, the limit from the graph.
1.
And at least do me the courtesy of waiting for me to write the rest of the question on the board. I'm teasing. Okay, so if we're walking towards 0, if we're walking towards 0 on the x-axis, we're walking towards 1 on the y-axis. And the same is true from here. Right, so from the graph, you just say, oh, well, even though there's not a definition for the function at that point, that doesn't mean that I can't walk towards it. And so that's why this ends up being 1. And so again, the fact that x never actually obtains the value 0 is critical in this instance. So just a note, you have no way of doing this algebraically yet. I haven't given you any algebraic rules. Right? So if you're trying to do stuff using algebra, how? And I haven't even allowed you, I haven't given you the rules for doing so. Okay, so let's do another example. What about, I'm going to let you think about this one for a bit. Let f of x equals sine pi over x. And let's just try to work this out numerically, right? Let's suppose we don't have a computer. We have no idea how this plot looks like. So let's just try some experimenting, right? Okay, so let's do the same thing that we did at the beginning of class. What is f of 1? Well, that's sine of pi. That's 0. Okay? What about f of 1 over 100? Or maybe 110. 1/110. That's going to be sine pi over 1/10, which is 10 pi, which is sine of 10 pi is?
0.7.
Where's sine 0? This is what?
Pi.
This is what? This is what? When sine 0? Sine is 0 at multiples of pi. Okay, this is calculus. This is pre-calculus. So please, you have to internalize these harder, right? Because I'm going to just flippantly, I'm going to have to be able to say sine of 10 pi is 0, right? Without explanation. So keep up on those worksheets. Okay, so what is f of 1 over 100 then? What is sine of 100 pi? 0. Okay. Any guesses for f of 0 then? Yeah, yeah, okay. So it would be sensible now to guess. Look, 1, 1/10, 100th. If I keep going, we're always going to get 0, 0, 0. So my guess is that f of 0 is going to be 0. This is a guess. But what? What's the mistake I made?
You put in the exact point.
Hmm?
You put in the exact point.
Well, no, if I put 0.1 into here, it would give, your calculator would give you 0. Yes, miss? Well, no, but this is the limiting procedure. I've tricked you. The evaluation points I've chosen will always give you 0, right? Because f at 1 over a is always going to be sine a pi, which is always 0. Okay? So I screwed myself by choosing if you did 5 over 100, right? F of 5 over 100 is sine of 100. That's a really bad example because that's divisible. 101, my favorite number. Okay. Sine of 5 over 101 is going to be 101 pi over 5. And this isn't equal to 0. Right, so what is happening? Well, we can use the stuff that we've learned to try and figure out what's happening. So, what's the effect of having sine and dividing x? What's the effect of this? If I have sine x over a, what is this a doing? If a is positive and greater than 1. Yeah, you got it. It's compressing it, right? If I do this, we're going to compress sine, right? So if I took this and I made this 4, right, you would get a whole sine thing within half pi. Okay. So what's happening here? Okay. As I make x go to, what was I even asking us to do? Yeah, limit as x goes to 0 of sine pi over x. What this is doing, as x gets smaller and smaller and smaller, we're compressing sine more and more and more. Right? So the function, I'm going to draw you the graph. And again, I'm going to do it over like a tiny region, -1 to 1. So this is what it's going to do. It's going to oscillate, but as it gets closer to the origin, you're going to get like infinitely many sine curves in here. And then this is going to come out again like this. So plot it. If you have sitting in front of a computer, you have your cell phone, plot it. Right? You're going to see that there's crazy behavior. Right? That means because every time we zoom into here, we're going to see infinitely many instances of sine curve getting infinitely compressed. But the point is any line that I run through here is going to hit the curve infinitely many times. I just happened to choose one that went through here. Anyways, that may have been kind of hand wavy, but the point is don't always trust your calculator because you can make human errors which hide the actual behavior of the function itself. So plot it, someone plot it. If you don't have a computer, look towards your partner because this one's kind of hard to draw by hand. Got to pick up the pace, people. Okay, one-sided limits. Okay, so in summary, if you have the graph, it should be easy to read off the limit except in crazy cases like that. So be careful, but liberally use Desmos when doing your homework. One-sided limits. Here's an example. Tons of examples in this class. Did you guys learn limits in high school? So this should mostly be review, yeah? No, you didn't learn limits in high school. Oh. I mean, that's fine. I thought I'd be boring everyone. Okay, so I'm just going to show you something called the Heaviside function. This is useful in statistics and other things because it allows you to turn something on or off, essentially. It looks like this. So this is the y-axis, the x-axis runs out here. And this is the point, this is at y equals 1. Okay, so what's the definition of this function then? So it's f of x, Heaviside function is actually denoted like this. Heaviside function of t, this is going to be, what is it? 0 if t is less than 0, strictly, right? So this is 0. And then 1, okay? Now, pay attention. Normally, okay, I'm going to write otherwise exactly once. Okay? If I write two conditions, and I write the first one, the second thing is always not that. Okay, so this is always otherwise. And so if t is less than 0, go to this one, and if it's not, it's this one. So in this case, this would be t greater than or equal to 0. But this is a redundant thing, so I'm not going to write it. Okay, what then is the limit as t approaches 0? So let's ask ourselves what we were defining the limit as. So as I walk along this line, what y value am I approaching?
0.
0, exactly. As I walk along this line, what y value am I approaching?
1.
1. Okay, that's a problem. Right, so I can't say I'm heading to both 0 and 1, right? In mathematics and calculus especially, we're worried about things being functions, by which we mean we want the answers to things to be one answer. You can't say the limit is both 0 and 1. It has to be one of those things. So in this instance, we say the limit of t goes to 0 of this Heaviside function does not exist. Right? Does not exist. Which is totally different than the limit going to infinity, which we'll discuss in a bit. This does not exist. The answer has to be one quantity. Okay, however, we still have the left and right limits. Because as I said, if you're walking along the... Jesus, Murphy. That is the worst sound in the world. If we're looking at the limit as t goes to 0 from the left, that's going to give us 0. And if we look at the limit as t goes to 0 from the right of this function, and we're going to get a 1. Okay? So what I mean by 0 from, so remember, we're trying to approach t equals 0. Here's t equals 0. So this is the real line. So t here, and this is where it's positive. If you're bigger than t, this is called t plus, t to the right, right? It's called the right because we're on the number line, and that's right of the number line. If we're approaching t, actually that's arrow should be going the other way. If we're approaching t equals 0 from the left, that means we're coming from this side of the real line, the left side. So this is t minus, right? This means, right, this region here is exactly the t plus epsilon, t minus epsilon region that I was indicating with the strict definition. Right, so t, this means 0 from the left, this means 0 from the right, and left and right in this context means which side you're approaching the value from on the real line. Okay, so why don't you try and think about how then we should define the left-hand limit, right? Because I defined limit generally. Now we want to restrict it to the side limits. So think about how you could modify the definition that I've given you already to be a definition for the one-sided limit. Circles, that's the C. Wax on. Okay. Okay, so here's the definition. Definition. This is going to be the left-hand limit. And this is going to be the good enough definition that we're going to use. So we say the limit as x approaches a from the left of f of x is equal to L when, and then some English, x approaches a from the right on the real line, which I'm just going to draw a picture here. So here's your real line. Here's your value a. And if we approach a from the, well, I was going to put this. No, I can't. Left-handed limit from the left. So that means we have x, right, coming from here. So this is going to be approaching a from the left. Okay, so fundamentally that means when you're reading on the graph that you can just like cover up the right-hand side of the graph and read a limit like that. So now I'm going to give you the definition. So I'm not going to write the right-handed one because it's obviously just change all instances of left to right and minuses to plus. But just for fun, I will give you the definition of the right-hand limit. The strict one, which again, you do not need to understand nor use. I just want to show you once. Okay, so this looks like this. So the limit as x approaches a from the right of f of x is equal to L. And I need a different piece of paper. Okay, when, and I'm going to write a real scary statement. When for any tiny epsilon you can find a tiny delta such that if x is restricted to this region, then f f of x is restricted to this region. And again, you will not be tested on this. It's just, I love stuff like this. This to me is a beautiful statement because so much is codified into one line. This is like so important to calculus, like this definition, right? I could actually say to you, prove it. Prove to me that the limit goes to this. Prove to me that it satisfies this condition. Right? Because we don't just, I'm not just throwing you things that calculus that we feel should be right. I'm teaching you the things about calculus that we discovered to be true because of other things that were true. Right? This is math. It's not what's the answer to this, what's the slope of this line. It's what assumptions have we made and what subsequent assumptions are consequent to those. All right, so I'm going to give you a question now after defining what a limit is. So this is going to be an important nuance, and I'm definitely going to try to trick you on your midterm. So I'm warning you ahead of time of this trick. So what will the trick be? I wonder. Okay. The limit as x goes to a of f of x is equal to L if and only if. Right, this symbol means if this is true, then what I write down here will be true. And if what is here is true, this will be true. So the limit of x goes to a of fx is L if and only if the limit of x goes to a from the left is equal to L, and the limit of x goes to a from the right of f of x is equal to L. This is important. So important that I'm drawing a box around it and putting a star beside it. When is it the case that the limit exists? It exists only when the left limit exists, the right limit exists, and in addition to those limits existing, they must be equal. Right? So in the case of the Heaviside function, which I erased, we had a left limit, it was 0. We had a right limit, it was 1. Those limits are not equal, so the Heaviside function in itself has no limit. Right? So two things you can conclude from this. If I tell you the limit exists, you know for sure the left and right limits also exist. If you know the left and right limits exist and are equal, then you can conversely conclude that the limit exists. So if I ask you a question on like your midterm that says, here's a function, its left limit is this, its right limit is this, you should be able to answer the limit of the function is then this. Okay, so question. This is one for you guys to do, but you'll probably be able to do most of it very quickly. So I'm just going to draw you a plot. Let's say that this is the point 1, 3. This is the point 1, 2. This goes down like this and up. Let's call this function g. Let's say this is 5, 2. This is a graph. So this is going to be 2. This is 1, 2. That's 1, 3. So it's going to be 1. Read the following. Read the following from the graph. All right. G of 1. G of 5. Limit of x goes to 1 from the right. Of g. Limit of x goes to 1 from the left of g. Limit as x goes to 1 of g. And limit x goes to 5. X goes to, x. Whoops. That should be 5. Limit x goes to 5. All right, take a second to do that. It should be easy. I'm going to have a drink of coffee. Make a lap. Check the recording's still going.
We're good.
All we hear is radio dial. You got it yet?
Sir.
Okay, G of 1. That's this guy, yeah? What's G of 1?
Does not exist.
Does not exist, right? Because look, it's either 3 or 2. It can't be both. So I'm not going to say it doesn't exist. I'm going to say it's undefined. Okay? Not existing is a very special piece of terminology that applies to limits. Undefined is a very special piece of terminology that applies to functions and being defined or not. Okay, what about G of 5?
Undefined.
Also undefined, open circle. Limit of G as x comes from 1 from the right. Okay, so let's look at this. Here's 1. Here's the right side of 1. So if I'm walking towards the right side of 1, where am I heading to and why?
2.
2. Same question, but from the other side, right? If I'm walking to the left of 1 along this curve, where am I ending up and why? 3. So then what is the limit as x goes to 1 of g?
Does not exist.
Does not exist, right? Despite the fact that the left and right limits exist. What's the limit as x goes to 5 of g? So that means I walk towards 5 along this curve. Where do I end up on y?
2.
What happens if I walk along the right, from the left-hand side to the point? 2. So they're equal. So this is 2, despite the fact that the function doesn't have a value there. You could still have that as a destination. You can walk towards a hole without falling in the hole, provided you don't step in the hole. That's actually not a bad analogy, because that's a hole. Right? You can walk towards the hole, don't step in it. Okay. We're getting there, we're getting there. 40 minutes. Infinite limits. Infinite limits. What's this number? Or what is this? Huh? Give me a definition. What's that? What is it I wrote on the board? You've been using it a lot. It's infinity, but have you ever thought about what it is? It's not a number. It can't really ever become infinity. Right? It's a concept. It's just a concept. And it's a concept that I've got to flesh out now. Because you shouldn't have ever really used this before you had limits. These symbols should only appear when we are using limits. Otherwise, this doesn't make sense to use infinity without a limit. Okay, so erase that. Here's just an example. Okay, here's f of x. Let's say that that's 1 over x squared. So what point is excluded? 0. So we just always notice, we don't have 0 in the domain of f. right? So just remind yourself that you shouldn't be drawing it if you try to. I'm going to show you what this function looks like. It's fairly standard. So if you think about this, if I make x really big, this number becomes really small. It definitely goes through the point 1, 1. It's even, right? So you're going to get the same function on the other side. Minus 1, 1. And as you become fractional, if I put a half into here, you're going to get 1 over 1/4, which is 4. If I put something smaller like a fifth, you get a 25th. So as the numbers get closer to 0, the function gets big. So you have something that looks like this. And something that looks like this. Okay? So now, I want to ask about the behavior as x goes to 0 of this function. And the amazing thing is that strict definition I gave you works even when the limit becomes infinity. I'm not going to talk about that anymore because that should be for a real analysis class. But all of this just it ends up working. You can go all the way to the very basics of mathematics, and this is all justified. Now, let's think about this question. Right? If I walk towards 0 on the x-axis, where am I heading to with respect to y? Huh? Positive infinity. Let me say left. This should be positive infinity. So this is important, right? This is important that x never actually gets to 0. Because the function never actually gets to infinity. It's approaching infinity, but it's not equal to infinity. Those are two entirely different. Nothing's equal to infinity. It's a concept. It's just the biggest number. Or you can only ever approach it. So if you ever use this, there should be a corresponding limit somewhere in your computation. It can only ever come as the result of a limit, or can be in here, which we'll talk about next class. Okay, we also have the limit as x goes from the right of this function. That means I'm walking towards 0 from the right. Where am I heading to in the y? That's also positive infinity. And given that these two limits are equal, and they exist, these limits exist. And there's a little nuance here. Like, it depends who you ask. Some mathematicians will say, this doesn't exist because infinity doesn't exist. But I think that's confusing. Right? I'm going to say these limits exist. I can write them. They're going to infinity. So here, we have that this implies the limit as x goes to 0 of this function is positive infinity. You don't have to write the positive. I'm just doing it there to emphasize that it's not the negative one. All right, so again, here, what did I write? Yeah, the limit of x goes to 0 of this function equals positive infinity. So approaching infinity is different. Approaching infinity is different than equaling infinity. Right? That's the whole purpose, right? So these infinities should always come with limits, right? Because it's just a concept that you can approach. It doesn't make sense to use it as a number, so just keep that in mind. I want you now to think about this example. Why don't you go ahead and on your paper, investigate the limit of x goes to 0 of 1 over x. Oh shoot, I meant to shift it by 5. That's okay. Okay, so I wrote that a little bit wrong. Just for the sake of difference, I'm gonna do this one. Okay, f of x is equal to 1 over x minus 5. Just, I don't know, I'm getting bored of centering things at the origin, right? So
Yeah, so just that.
here we immediately notice that 5 is not in the domain of f.